Hi everybody, this is a lecture on section 7.3, polar coordinates. So, in the xy plane, or in the two-dimensional plane, each point is represented uniquely by a pair x, y, right? So, right, like 3, 2, one, 2, 3, 1, 2, right? This is the point 3 on the x-axis, 2 on the y-axis, or 1 minus 2, so on and so forth. So these coordinates or this coordinate system is called Cartesian or rectangular coordinates. However, there is another coordinate system that is often very useful. So another way of identifying points is by using polar coordinates. So in polar coordinates, you have a point here, and that point lies along, right, some particular line through the origin, right, and there's an angle of rotation from the positive x-axis, and then there's a certain distance along that line from the origin. So this distance, we call it r, this angle we call it theta, and therefore this point is r theta. Okay, similarly, you can also go down here. So if this distance here is r, you can also call this point minus r theta. So that's r units out on that angle of rotation. This is r units in the opposite direction through the origin. But you'll notice that r minus r theta is also positive r theta plus pi. So it's the same as positive r theta plus pi. And this is the same as positive r theta plus 2 pi. So there's not this uniqueness of representation for points. So points are not represented uniquely by a pair r theta. However, r theta plus k pi, where k is odd, where k is odd, and r theta plus 2 pi L 2 pi well, let's just try L pi, where L is even, are the only two ways to vary. Then non-uniqueness enters. Non-uniqueness manifests itself. Okay, so every point is represented by a pair r theta, and as long as you assume r is positive and theta is between 0 and 2 pi, some rotation of 360 degrees, then points will be uniquely represented by polar coordinates. Not that you necessarily always want that, but you can have it. All right, so for example, or no, before that. Before we go into an example, let's talk a little bit more about the point r theta and its relationship to xy. So if this length is r, again, and this angle here is theta, right, then this is the point r theta. Notice that the x coordinate here, right, this length right here is x, and this length right here is y. Right, so x is r cosine theta, and y is r sine theta. Therefore, x squared plus y squared equals r squared cosine squared theta plus sine squared theta. So that's just equal to 1. So x squared plus y squared is just r squared. And y over x is equal to r sine of theta divided by r cosine of theta. So the r's cancel, and you just get tangent theta. Okay, so these are the standard relationships between rectangular and polar coordinates. Okay, x is r cosine theta, y is r sine theta, x squared plus y squared is r squared, and y over x is tangent theta. So, for example, so here is a point 5 pi over 3. Convert to Cartesian coordinates. Well, x is equal to 5 cosine pi over 3, right? And y is equal to 5 sine pi over 3. So this one is equal to 5 halves, and this one is equal to 5 root 3 over 2. Okay, so, that's one way to convert from polar to rectangular coordinates. Another example, let's go the other way. So say we have this point here for 3. So this is the point 4, 3. Convert to polar coordinates. Well, the distance from the origin, r, is equal to square root x squared plus y squared. So that is equal to 4 squared plus 3 squared, which is 5. So r is 5. And then the theta is equal to, well, tangent theta is equal to opposite over adjacent. Opposite is the length of this, which is the y-coordinate, over x, right, which is the x-coordinate, this length, right, because that's a right angle. So theta is equal to arc tangent 4/3. Right, so this point here uh, 5 arc tangent 4/3. Okay. One moment. Okay, so now an equation relating r and theta will, like it does with equations relating x and y, will define a curve in the two-dimensional plane using either x and y coordinates or using polar coordinates. So polar equations. So an equation relating r and theta, creates a curve in the two-dimensional plane just as an equation for x and y creates a curve, period. So here are some basic ones. R equals, so no theta in this one, just r. R equals 3. So you're just specifying r equals 3, right? Like, I mean, you specify, say, like x equal to 5, right? And that gives you just a vertical line through 5 on the x-axis. What does r equal to 3 give you? Well, that just defines all points whose distance from the center is 3, right? Whatever theta might be, right, that gives you the circle of radius 3. So all the different points at radius 3. Right, so this is the circle of radius 3 centered at the origin. Well, it's not a very good circle I've drawn. Bulging out a little too much there. That's a little better. How about if we just specify theta? Theta equals pi over 5. Okay, well, if theta equals pi over 5, then, and r is unspecified, right, that would be all points on this line whose angle of rotation from the positive x-axis is pi over 5. So it's a line through the origin where that's the angle. So r is anything, and pi over 5 is the angle. So that gives you this whole line. R equals 3 with no specified angle gives you this disk through the center. or sorry, the circle centered at the origin. All right. How about equations with r and theta? How about this? So let's say r is equal to theta for theta bigger than 0. Okay, what does this look like? Well, think of different values for theta, right? Here's theta like 10 degrees, 45 degrees. So I mean, here's increasing values for theta. All right, increasing values for theta give you these lines through the origin. One, 2, 3, 4, so on and so forth. Right, and the r value for different values of theta, right, these r values are smaller, getting bigger, getting bigger, getting bigger, 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 right? So it creates this kind of effect here and gives you a spiral, right? As theta increases, r goes along with it, and then you get this kind of spiral shape. Oops, let me try to put those dots in a better place. There we go. Probably my picture is not increasing quite fast enough, but there it is. Okay. So r equals theta is a spiral. You could also have, say, r equals square root of theta. R equals any increasing function for theta. So r equals square root theta, r equals natural log theta, r equals f of theta, which is just some increasing function. All yield, where f is an increasing function, all yield different kinds of spirals, although spirals don't either open up faster or slower, depending on how fast the function f of theta is growing. All yield spiral like this one. Okay. What else? Some more varied type things. How about something like this? How about just r equals cosine of theta? R equals cosine of theta. Well, what's the graph of that going to look like? Well, cosine of theta, of course, varies between 1 and -1. And let's look at it in chunks of 90 degrees as it jumps from 0 to 1, back to 0 to -1, back to 0, so on and so forth. So from 0 degrees to pi over 2 degrees, or radians, excuse me, cosine theta goes from 1 down to 0. And then from pi over 2 to pi, it goes down from 0 to -1. And then from pi to 3 pi over 2, it goes from -1 back to 0. And then from 3 pi over 2 to 2 pi, it goes from 0 back up to 1. So what does that look like? So here's 1, here's 0. So as we go from 0 to pi over 2, we're going through these angles. Okay, and the function r equals cosine theta is decreasing during that time. So smaller, 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 smaller here. Excuse me. There we go. No, it still doesn't look right. There we go. And then from 90 degrees to 180 degrees, so these angles here, we're going from 0 to -1. Right, so here's the opposite angles through the origin, since my r's are negative. Right, we're going from a radius of 0 up to a radius of 1 as these angles are increasing. See, as the angles increase, the radius outward gets bigger. So I'm left with something like this. All right, and then as we go from pi to 3 pi over 2, we're going to sort of retrace over this. So it seems like we're getting a circle. Can we prove this is a circle? Well, this is the graph r equals cosine theta. So if I multiply both sides by r, I get r squared is r cosine theta. Right? R squared is x squared plus y squared is equal to r squared cosine squared, or no, sorry, r cosine theta. But r cosine theta is just x. So now I've got x squared minus x plus y squared is equal to 0. So I have x squared minus x. Take this coefficient, divide by 2, which is a half, and then square it, and you get 1/4 equals 1/4. So this is x minus 1/2 squared plus y squared equals 1/4. So this is the equation of a circle, the Cartesian equation of the circle of radius 1/2 centered at 0, 1/2. Or, I'm sorry, 1/2, 0. Which is exactly what I got over here. This is exactly this picture. Well, what is suggested by that picture. All right, let's try another example of a polar equation. How about r equals sine 3 theta? Okay, so with r equals sine 3 theta, again, sine theta varies from 0 to 1, back to 0, to negative 1 to 0, back to 1, so on and so forth. So I would like for sine of 3 theta to go in increments of 90 degrees, right? So I'd like it to go from 0 to pi over 2 to pi to 3 pi over 2 to 2 pi. That should be sufficient, I think. So that sine of 3 theta goes from 0 to 1, back to 0, to negative 1, and back up to 0, right? We would like sine of theta to go in steps of, 0 to 1, 1 to 0, and unit steps like that. So 3 theta, the argument for sine 3 theta, needs to go in steps of 90 degrees. Therefore, theta goes from 0 to pi over 6. To 2 pi over 6, which is pi over 3, to 3 pi over 2, or pi over 2. So these are steps of 1/6, 1/6, 2/6, 3/6. And then, so that's 3/6, 4/6, would be 2 pi over 3. So every 30 degrees, we're going to jump from 0 to 1 to 0 to negative 1, so on and so forth. So let's mark those off. Okay, here is 30 degrees. Here is 60 degrees. Here is 90 degrees, right? And let's draw the lines all the way through the origins. So just as a guide to see what this is going to look like, get some sort of rough sketch. Okay, so we're starting at r equal to 0, theta equal to 0, going out to theta equals pi over 6, pi over 3, and then to pi over 2, 3 pi over 2, 2 pi over 3, 5 pi over 6, pi, which is 6 pi over 6. So here we're going from 0 to 1. So that's 1 comma pi over 6. 1 comma pi over 6. And then from 1 back to 0. From pi over 6 to pi over 3. And then from here to here, we're going from 0 to negative 1. Right, so we're going to be down in here. And then from negative 1 back to 0. Between here and here. Right, so we went from 0 to 1 for the first 30 degrees, 1 back to 0 for the next 30 degrees, 0 to negative 1 for the next 30 degrees, which was in here, negative 1 to 0 for the next 30 degrees, which was in here, and then 0 to 1 for the next 30 degrees, which is in here. I went out a little further than I needed to there. And then from 1 back to 0 in the next 30 degrees, which is here. And then after that, we're going to go from 0 to negative 1. So it seems like we're going to retrace the same thing. So it seems like that is, what this thing should look like. And this is called the 3-leaf rose. R equals sine 3 theta. So I lifted a picture from Wolfram Alpha. right? So there it is. There's the one that the computer generated. So let's stick that in the doc. And this one is doing theta from 0 to 2 pi. So it retraces itself quite a bit. So here's the picture. I think I squashed it a little bit too much. So here's the illustration from Wolfram Alpha. And, you know, those illustrations will be a little bit helpful for us later. So in Wolfram Alpha, enter polar plot r equals sine 3 space theta, like that. And it'll know what you're talking about, and it'll give you this picture here. So when you want to do polar graphs, just, you know, theta, just write out theta, and it'll know what you're talking about. Okay, so that's a pretty famous graph in polar coordinates. And, you know, whereas the circle that we just looked at back up here, you know, has an equation that's recognizable in rectangular coordinates, you know, this one is really not going to have something recognizable in rectangular coordinates. Translating it to rectangular coordinates is really going to be, really going to be difficult. But we can give it a go. But it's not going to be something that you recognize. Certainly you've never encountered that. Let's try converting r equals sine 3 theta to rectangular coordinates. Right, so let's use this formula here, is that sine of a plus b is sine a cosine b plus sine b cosine a. Right, so this gives me, because we can't use 3 theta, right, because x is equal to r cosine theta, and y is equal to r sine theta, not 3 theta. The 3 theta is not helping us out here, so we got to get everything in terms of theta. So what do we have? So r equals sine 3 theta is equal to sine 2 theta plus theta. So this is equal to sine 2 theta cosine theta plus sine theta cosine 2 theta. And then sine 2 theta is 2 sine theta cosine theta cosine theta plus sine theta, and then cosine 2 theta, it was, well, we'll use the cosine squared, we'll use this form. Alright, so it may look a little hopeless here, but it's actually not. So what do we have so far? So far we have r is equal to 2 sine theta cosine squared theta plus sine theta cosine squared, so there'll be 3 of those, minus sine to the 3rd theta. So I've got 3 factors in each term here. 1 sine, 2 cosines, and then 3 sines. So what I'm going to do, multiply both sides by r to the 3rd. So r to the fourth is equal to 3r sine theta, r squared cosine squared theta. So each trig function gets its own r. So those all become x's and y's. R to the fourth, right, that's r squared squared. 3r sine theta, r cosine theta, that whole thing squared, minus r sine theta, this whole thing cubed. So I got x squared plus y squared squared is equal to 3yx squared minus y to the third. So there it is. I don't know really how to make, any sense of that. I mean, that's not something we've really ever seen before. But I mean, if you were to encounter this in rectangular coordinates, you'd just, kind of throw up your hands and say, what's that? Right? Maybe I would, but certainly this is a lot simpler. Right? So even though you can express this in Cartesian coordinates, polar coordinates is a much more natural choice. You just get these really beautiful graphs. All right, so there's a lot more examples we can do in this section, which we'll do during discussion, and also in the next section there'll be more graphs that we can draw and analyze using derivatives and integrals. So we'll end the lecture for this section right here.